Welcome to your next period of instruction. This period of instruction is primarily going to be focused on nucleosynthesis, but because of how closely related a couple of other topics are to it, we're going to be covering them as well. Those other two topics are going to be nebular theory and core accretion theory. It's unfortunate, but it's necessary. There are several learning objectives, but we'll be splitting them up by topic to keep it simple, starting with nebular theory, which is the explanation of how stars are born. The learning objectives here are to be able to describe how stars accrete matter, how they ignite, and what sustains them. So, stars are made from gases, like hydrogen and helium, which in space you would think would simply dissipate, but that isn't the case. See, all physical matter, including gases, exerts a pull on everything else around it through gravity. A larger collection of matter exerts a larger pull on adjacent objects. This applies to gases and dust as well, which gather in nebulas. Gravity is a key component, but it isn't the only one. A degree of friction and velocity is needed as well. Interactions with other mass through gravity causes rotation, which, as the gas and dust condenses down, spins faster and faster, much like a figure skater pulling in their arms and legs, and you see them start to rotate faster. It's the same principle here. Up to this point, we've only formed a protostar, a gaseous mass that has not started undergoing fusion yet. Once the protostar gains enough mass, friction, and angular velocity, then when atoms collide, they can fuse into heavier elements. This releases massive amounts of energy, adding to a chain reaction that ignites the star. That brings us into the main topic of nucleosynthesis, which has its own set of learning objectives. What types of nucleosynthesis there are, what elements they produce, and how they go about this. Nucleosynthesis is the process that forms the naturally occurring elements. We'll talk about the difference between natural and artificial elements in a bit. We talked about some of element formation last time when we were talking about the Big Bang. Remember that the source of the cosmic microwave background radiation is the energy released from the formation of the lightest elements when electrons and nuclei were coming together. This is what is known as Big Bang nucleosynthesis, which formed hydrogen, helium, predominantly, with traces of a couple of other light elements. The process involved was the interaction of the strong and weak nuclear forces, resulting in the formation of basic nuclei, which only had a couple of protons and neutrons if they're heavier than hydrogen, and all of them utilized electromagnetism to capture electrons. We'll cover these forces in greater detail in the next period of instruction. For now, you need to know this. The strong nuclear force is what binds the nuclei of atoms together. Electromagnetism holds the electrons in orbit around the nucleus, and the weak nuclear force prevents those electrons from coming all the way into contact with the nucleus. Once these light elements formed stars, stellar nucleosynthesis took over. Stellar nucleosynthesis is where we start getting heavier elements through the process of fusion. Stars are massive stellar bodies, and many stars are much larger than our own. Gravitational pressure and the heat caused by it, along with some friction and the sheer momentum of these atoms and other fusion reactions happening in the general vicinity, agitate the atoms to such velocities that when two of them slam together, they fuse into a heavier element. When this happens, they release a tremendous amount of energy. Elements up to and including iron are made this way. These elements divide themselves into layers as the star ages, with the heavier elements forming the core. Stars more massive than ours can fuse up to iron, which is effectively stellar ash, with the payoff from fusing it no longer sufficient to fuel the reaction even if they could fuse. Now, the sun in its entirety is fighting against gravity at the core, and the thing holding it away from the core is the constant fusion of elements. As the star's fuel is used up and the fusion of heavier and more dense elements becomes more common, the resulting increase in energy and runaway fusion that it causes will cause the star to expand into a red giant, as ours will do. The expansion will be pretty quick and blow off the lighter outer layers and take our planet with it in the process as it expands into our orbit. Anyway, gravity is still trying to pull all the material back to the core, and the accelerated fusion will not last forever. Eventually, gravity will win out, and all of the star material will come crashing back down. The rebound of the impact will dissipate the remaining gases and blow off most everything lighter than the core itself, which will be left behind as a white dwarf star. Our star remnant will be made of mostly carbon and oxygen, gradually dissipating thermal energy as light and heat since it's no longer able to fuse those elements into heavier nuclei. It will have a mass of about half that of the sun in its current state, but with a volume around that of our planet, like most white dwarfs end up. Supernova nucleosynthesis is the last type we will be discussing. Nova and supernova are two completely different phenomena, with the difference being the amount of energy released. Novas don't have the energy needed to fuse elements heavier than iron, but supernovas do. And when they go big, creating a light that outshines entire galaxies, like this one, SD 1994D, the bright spot in the bottom left of this image. A supernova can happen in one of two ways, either when a star hundreds of thousands of times larger and more massive than ours collapses, or when a white dwarf goes into runaway fusion by stealing matter from other stars. Stars come in a variety of sizes, with our own, as large as it is, actually coming in on the small side. Massive stars live their lives very similar to our own, with the difference being in how they die. These stars can fuse up to iron, and if there's enough material to fuse into iron, eventually that iron core will become so massive that it will collapse under its own weight. This is a very sudden crunch, and the shock wave created from the core collapse and the rebound of material impacting it causes the rest of the star to explode in a supernova. These massive stellar explosions create nebulas of materials comprised of all the elements that made up that star when it died. More often, we see a different type of supernova, though, resulting from a white dwarf in a binary relationship with another host star. Now, this white dwarf is in a close enough proximity to siphon off material from its companion. When enough material is accreted on the surface of the star, it undergoes that same runaway nuclear fusion. That results in a massive explosion and release of energy. These can be repeat events and happen in cycles that can be predicted and tracked from the star responsible until one of two things happens. See, when the white dwarf is stealing matter from its companion, it's not fusing it's fusing all of it, but it's not blowing all of that off. Some of it stays on the surface. Eventually, it will gain enough mass to have one of two things happen. Either it will turn into a neutron star, or it will take it a step further and become a full-on black hole. Now, both of these types of supernova can create the rest of the naturally occurring elements. The difference between natural and artificial elements is that the artificial ones can only be produced in particle accelerators, admittedly in very small amounts. Now, like I said, these explosions throw out a lot of debris, enough to form not only new stars that can be born in the ashes of their predecessors, but planets as well, which is where core accretion theory comes in. The learning objective of this theory is to be able to describe how planets are formed, and it's a very straightforward process. Nebulas of gas and dust clump together in the accretion disk of a protostar. Before or after the star ignites, around the same time, because bear in mind all of this is happening simultaneously, clumps of dust gather, attracting more and more material until a body of around 100 kilometers or so is formed, at which point it becomes effectively dominant in that part of the accretion disk, dominating that area with its gravitational influence and becoming a protoplanet. Now, this gravitational influence traps gases as well, forming the beginnings of an atmosphere. The composition of a planet is dependent on the material around it, so gas giants are formed in the same process. And with that, this concludes your period of instruction. Your next period of instruction will be getting a grounding in geology, and we'll start with radiometric dating.